This video is an introduction to the capacitor in a nutshell. We will start with a typical problem you often find in electronics, which is called a bouncing button, which makes a connection multiple times after it has been pressed only a single time, which means that your circuits probably won't, sometimes at least, won't work as expected. And in the process of solving this problem, I will show you what a capacitor is, how its charging and discharging cycles look like, and how you can build one yourself from 2 pieces of aluminum foil and 2 laminating pouches. And by the end of this video, you will know how you can use and also dimension capacitors to mitigate the impact of noisy signals in your circuits, for example, to debounce a push button in an Arduino circuit. My name is Andreas from The Fearless Engineer, and here we go. If you have seen the last video on how to build an Arduino-based traffic light, you already know how to connect and control LEDs to the Arduino board. If not, here's a link to the video coming up for you. And as you can see here, 2 LEDs are connected to the output pins of the Arduino, and a push button is used to start the control cycle. Let's now look at a new project which uses the same basic components, which are an Arduino, LEDs, resistors, and a push button to build a counting device. In the simulation here you can see the Arduino with a power supply and a reset switch on the left, and with a large number of LEDs and also resistors on the right side. In the current state, all LEDs are switched off, but as soon as I press the push button on the right, a single LED in the bottom row lights up. And when I press again a few times, the bottom row is eventually full, and when I now press once more, the bottom row is turned off again and a single LED in the top row is switched on instead. So for every 5 button presses, an LED in the upper row lights up. And in the current state, you can see the counter shows the number 17, as each of the upper LEDs represents 5 counts, plus the 2 single counts you can see now in the bottom row. So in theory, this seems to work just fine. And by the way, in case you're interested in the source code to the project, I will leave you a link to it in the description of the video down below. Now let's take a look at the real circuit, and what you can see here is exactly the same as in the simulation we just looked at. On the right there are the 2 rows of LEDs, in the middle there is the push button with its pull-up resistor, and on the side you can see an Arduino Nano, which works just like an Arduino Uno but is a lot smaller. And in case you're not familiar with some of the components you can see here, for example the pull-up resistor, you might want to check out my playlist on the traffic light project. The link is coming up for you right now. But let's now power up the circuit and do some counting. And you can clearly see that for each time that I press the button, another LED lights up, just as in the simulation. But once in a while, the counter increments several steps at the same time at once, even though I have pressed the button only a single time. So clearly something in the circuit here is not working correctly that differs from the simulation we just saw. So let's hook up an oscilloscope to the button input pin and see what happens there. And on the screen you can see that when I press the button, the voltage drops from 5 volts down to 0 to ground pretty quickly each time. But if you zoom deeper into the signal and increase the time resolution to, let's say, 2 milliseconds per division, you can see that some of the button presses do not cause a single drop to 0 as it should be, but instead they entail a whole series of ups and downs after the initial press. So for our counting device, this is bad news, because with each transition from high to low, the counter is increased by 1. And as you can clearly see in the example here, there are several additional transitions after the initial button press over the time span of, let's say, 2 to 4 milliseconds. So this is the problem we are facing here. How can we improve this circuit in a way that the single push of the button leads to a single counter increase only? And basically there are 3 ways to approach this problem. The first is you could install, let's say, a more reliable button, which might work most of the time, but even with high quality buttons, signal bounces, this up and down is called bouncing, signal bounces can never be entirely avoided. And the second solution could be to come up with a software solution instead, such as inserting a delay of several milliseconds after the initial press so that these spikes do not register in the code. And this solution is called a software debounce, and is actually seen very often because it's so simple to implement. But as with the software controlled pull-up resistor we have looked at before in another video, I believe that hardware problems should always have hardware solutions, so that in your code you can focus on the actual algorithm without thinking too much about potential hardware implications, which is especially important when you're not working alone but in a team, because not every computer programmer is also an electronics expert and can understand the implications of his software commands on the hardware of the circuit. So the third solution we're going to look at is to use a so-called charge reservoir that stabilizes the voltage at the input pin when the signal bounces between high and low. And this is what this video is about, building a charge reservoir, which is also called a capacitor, to mitigate this bouncing effect. Well, let's take a look at the yellow signal first, which is the input pin voltage connected to the button. And as before, the initial press is followed by a series of bounces which would increase the counter. But there is now a blue curve as well, which you can see here, which slowly follows the yellow curve but does not drop to zero immediately. And when a spike occurs, you can see that the curve moves upwards in the direction of +5 volts, but not as erratic as the yellow signal does. So this is the basic idea. Let's build a charge reservoir that produces a stable voltage at high level when it's completely full, and when the button is pushed, the reservoir is discharged, is drained slowly to ground over a defined time span we can control, and which should be in the area of around, let's say, 2 milliseconds to 4 milliseconds, taking in the transition from high to low state. And when the button is released again, the reservoir should recharge to high, so it is ready for the next button press. But how can we build a charge reservoir, and what does charge have to do with voltage? In order to understand this, let's briefly revisit Coulomb's law again, which quantifies the amount of force between two charged particles. And if you're not familiar with this law, you might want to revisit the video I have made on this topic. The link is coming up for you right now. And as you can see on the slide, Coulomb's law describes the force between charged particles somewhere in space. So when you place two charges in a distance r to each other, they will either attract or repel each other based on the sign of the charges. And when we consider only a single charge and remove one q from the force equation, we get the electric field of this charge that describes its potential to interact with other charges that might occur somewhere in space. So this is the basis for building the charge reservoir. Now let's take a look at two examples for arranging charges in space. And for simplicity, we assume that the electric field is equally distributed and that there are no nasty side effects and edge cases we need to consider. So for a point charge, the case is very simple. When you place a sphere around the charge, the field will penetrate the sphere evenly over the entire surface area, which is, in the case of a sphere, 4 pi times r squared, which is exactly the expression by which we divide the equation here. The surface area of the sphere in a distance r from the charge. So the generalized form of Coulomb's law states that if you divide a charged body by the surface area that encloses its charges, what you get is the electric field, which is why we can also use a set of charged metal plates, as you can see on the right here. And in this example, the electric field is entirely in between the plates and the field lines are all parallel. So we can easily imagine the field lines to penetrate the plate area, which is why the electric field of this setup here results in the ratio of plate charge Q divided by plate surface area A, while the term epsilon 0 times epsilon r expresses the permeability of the material in between the plates for the electric field. And in case of vacuum or air, epsilon r, the relative epsilon, can be assumed to be 1. So we now have a way to describe the electric field of a group of charges, and we have already seen that we can group them together in a set of metal plates. But how do we get from charge to voltage? Let's find out. As we have discussed in another video, the link is coming up here, there is a simple relation between voltage, charge and the electric field. And similar to an object with a mass causing a gravitational field, stationary charges cause an electric or electrostatic field. And when you consider an apple hanging on a tree, you surely know that the height of the apple above ground defines its potential energy in the gravitational field of the Earth. And in a very similar manner, the position of a charge in an electric field also defines its potential energy. And the change in potential energy between 2 points in an electric field is what we refer to as voltage drop, or just voltage. And we can describe this voltage drop as the product of the electric field E within which the charge is located and the metric distance between the 2 points, which is called d12. If you want to have more details on this topic, check out my video on electric power and energy. The link is coming up for you right now. So if we consider the set of charged plates again and assume that there is charge located on the plates, we can calculate the voltage drop U12 across the plates as the product of the electric field E that is caused by the charges and the physical distance d12 between the plates. And when we insert the equation for the electric field of charged plates from the previous slide, we get a very neat relationship between voltage and charge and the geometric properties of the plates. So the charges are the cause and the resulting voltage in this case is the effect. And if we can somehow manage to get charges to move onto the plates, we could in principle use the resulting voltage to stabilize the push button signal in the LED counter we have seen before. So let's see how we can move charges onto the plates. And luckily this can be done in a very simple way by just connecting the plates to a voltage source. And in the diagram, the positive terminal of a source has been connected to the left plate and the negative terminal is attached to the right plate. And for this setup, the cause-effect relationship is reversed and we can write the charge on the left side of the equation and the voltage on the right side. So the voltage pulls electrons away from the left plate and makes them flow towards the positive terminal. And when this happens, we get a deficiency of positive charges on the left, which creates an electric field through the material in between the plates so that it attracts negative charges onto the right plate from the terminal of the battery. So over time we have a buildup of negative charges on one plate and of positive charges or a deficiency of negative charges on the other plate. And as we have established already that an electric field causes a voltage drop, what we get in this case is a rising voltage level between the two plates. And as you surely know, the device we have been discussing so far is of course called a capacitor. So before we get to integrating one of these devices into our circuit, let's find out how we can express its capacitance for storing charges in an equation. We have already seen that the amount of charge depends both on the voltage source to which we connect the capacitor and on its construction parameters, which are plate area, plate distance and field permeability of the material in between the plates. So how can we find a good measure for capacitance? And one question we could ask might be, if we increase the voltage by a certain amount, how much charge would that add to the plates of the capacitor? And to answer this question, we could simply divide charge by voltage so that we get the equation Q divided by U, which is called capacitance. And it tells us the amount of charge we get for a certain increase in voltage. And as you can see, it only depends now on the material parameters of the capacitor itself. And once those have been fixed after the device has been built, its capacitance will not change anymore. And as with current and voltage and resistance, capacitance has its own unit name as well, which is called farad, after Michael Faraday, who is regarded as one of the most important experimental physicists of the 19th century. So let's quickly build a capacitor of our own and measure its capacitance. And to do this, we only need 2 pieces of aluminum foil and 2 laminating pouches. And let's now first laminate the first piece of aluminum foil and run it through the machine and make sure that a piece of it sticks out of the pouch so we can use it as a contact later in the circuit. And once we're done, we place the second piece of aluminum on top and put both pieces into a second pouch and laminate this pouch once again. And now we have our own do-it-yourself capacitor. Let's take a look at the parameters of the DIY capacitor we have built here to get a gauge, an estimate on the capacitance we can expect. So the surface area of one plate is 0.012 square meters and the thickness of the laminating foil is somewhere around 80 micrometers. And as it is made of plastic, we can assume that its permittivity for the electric field is somewhere in between 2 and 4. So even though there is some guesswork involved, we can insert the numbers into the equation we have derived and get to a capacitance of around 2.66 nanofarads, which is the ballpark number we should also see in the measurement. And typical values of capacitors you'll find in practice, they range from 1 picofarad up to 10,000 microfarads, which is 0.01 farad. So actually 1 farad is really large capacitor, which you don't find very often in practice. So let's set the multimeter to measure capacitance now and connect the measuring tips to the contacts of our homemade capacitor. And sure enough, we can see a value which is very close to the estimate we have just computed. The problem with this capacitor, however, is that it's very big and it's not very easy and convenient to integrate into a circuit, obviously. And for this purpose, we will use a small ceramic capacitor, which has a capacitance of 2.2 nanofarads, which you can see here on the side, which is pretty close to the one we have just built, so it will work just fine in our circuit. So let's now take a look at how we can hook up the capacitor to our button in a way that it stabilizes the voltage at the Arduino output. And in the diagram you can see the button without a capacitor first, and the resistor R1 acts as a pull-up resistor and draws the voltage at the free contact above the switch to plus 5 volts. And when the switch is closed, the contact is shorted to ground, which brings the voltage down to 0 volts. And the problem with this circuit here is that the signal, as we have seen before, can change erratically when the button bounces, when it goes up and down and closes the contact in a high frequency. We have already seen this on the oscilloscope. So in order to stabilize the signal, we can simply connect a capacitor and also a resistor in parallel to the push button, just as you can see here in the diagram. And depending on whether the button is pressed or not, this circuit here behaves in two distinct modes. Let's take a look at the first mode. When the button is in an open position, the capacitor is charged by the current that flows into it from the plus 5 volt connection through the two resistors R1 and R2 and onto the capacitor plates where charge is accumulated over time. And one very important property of a capacitor is that electrons do not flow through the capacitor, but instead they accumulate on the plates and simply stay there. And once the plates are full, the current flow comes to a halt as there is no space left where new electrons could eventually move to. And it is exactly this process of charge accumulation over a certain time period which makes the capacitor so interesting to us, because we can control this charging time by setting the capacitance C or the resistance value R or both. And when we increase the capacitance C, it takes longer to charge the capacitor because, for example, there's more space on the plates, because the area has been increased, or the distance of the gap in between the two plates has been made smaller, which leads to a greater pull of the electric field in between the plates, or we simply have another material in between which has a greater permittivity for the electric field. And if we resize the resistance as an alternative, we reduce the charging current, which also reduces the speed with which electrons flow onto the plates, which also increases the charging time. And in the diagram you can see 3 charging curves for different combinations of R and C, and all start with an initial voltage of 0 volts, and depending on the resistance and capacitance of the respective pair, the charging time varies significantly. We will look at the equation behind these curves in a future video, but for now it's sufficient for you to know that a smaller resistance and a smaller capacity lead to a much steeper incline at the beginning and thus a shorter charging time. And in order to estimate how long it will eventually take for a specific resistor capacitor pair to charge, you can compute the so-called time constant tau, which is simply the product of resistance and capacitance of R and C. And you can easily check that the unit of R times C results in seconds, because R is volts divided by amps and C is ampereseconds divided by volts, which leaves only the seconds. And interestingly, the charging behavior of every capacitor resistor pair results in a level of 63% of the source voltage after the time tau has passed. And after 5 times tau, the voltage across the capacitor will have increased to 99% of the source voltage, which is what the time until complete recharge of an RC pair is reached is usually computed as 5 times R times C, or 5 times tau. And for the green curve, which represents a 1 kilo ohm and 1 microfarad pair, 5 tau is equal to 5 milliseconds. Now let's take a quick look at the second behavior mode before we get to actually building the circuit. When the switch is closed, the capacitor and R2 are connected to ground, which causes C1 to discharge via R2. And as before, the time constant is defined as the product of resistance and capacitance. But in this case, R1 does not play a role for the discharging behavior because the capacitor charge flows directly to ground after passing through R2. And as you can see from the slide, I have entered the capacitance value of our self-made capacitor for both curves now, which is roughly 2.5 nanofarads. And as this is a very small value compared to the 1 microfarad we have seen in the other discharging curves, we need a large resistor to slow down charging and discharging to suit our needs, which is debouncing the button, which is an event that occurs over a certain period of time, roughly around 2 to 5 milliseconds. So for this particular combination of 2.5 nanofarads and 400 kilo ohms, we can expect a charge-discharge time of around 5 milliseconds, as you can see from the diagram here, which should be enough for the push button bounces we want to remove from the signal. So let's get back now to the circuit and add the capacitor to it. So let's now integrate the RC combo into the LED counter simulation from the beginning. And let's first remove the switch and place it next to the 10K pull-up resistor, and then add the 400K resistor for charging and discharging. Then we add the 2.5 nanofarads capacitor itself on the right side of R2. And it's important to use the position between R2 and C1 to connect the pin, because if we chose the position between R1 and R2 instead, we would still see the button bounces just as before. This would be the raw button signal. So when we now press the button a few times, you can see that the circuit, at least in the simulation, works just fine. Which means it's time to try it in practice and take a look at the real circuit now. So on the breadboard you can see a capacitor with a size of 2.2 nanofarads, which comes close to the homemade capacitor which we have built, and a 400 kilo ohms resistor right next to the push button. And let's now hook up an oscilloscope to the position between R1 and R2, which will show the raw button signal, including all the bounces. And the second probe goes to the position between R2 and C1, where I also have connected the input pin, and which now should see the smooth signal, hopefully without the bounces. And as soon as we close the button, you can see that the raw signal behaves just as before, but the new signal directly above the capacitor shows a nice and smooth behavior similar to our predicted curve. And as you can see, when a downward flank of the raw signal occurs, a bounce occurs, the voltage across the capacitor does not immediately go down to zero, but continues down on its smooth downward slope. And when the raw signal bounces up again, the capacitor also reacts with an upward movement because it is recharged again, but not as fast as the raw signal does. And we could easily slow down this recharging speed here by using a larger capacitor in the area around 1 microfarad, for example, because in this case we could change R2 to a value around 1 kilo ohm. So we would discharge the capacitor with 1 kilo ohm and charge it with 1K plus the 10K of the pull-up resistor, which is a ratio of 1 kilo ohm for discharge and 11 kilo ohms for charge. And this would lead to a much slower charging curve, as you can see from the graph here. In this video you have learned what a capacitor is and how its capacitance is determined by the surface area, the plate distance and the permeability of the material in between the plates. And also you now know how the charging and discharging cycles look like and how you can control them by combining the capacitor with a resistor. And the button debouncing we have performed is indeed a low-pass filtering. We have used the RC combination to remove the high-frequency bounces from the switch signal and permit the low-frequency change we got from the button press. And filtering out unwanted frequencies from a signal and permitting others is one of the major use cases of capacitors. And when we combine capacitors with other components such as inductors, for example, a large variety of applications opens up to you: high-pass filtering, band-pass filtering, low-pass filtering and many others, but this is something we will look at in future videos. So if you like this video here, leave a thumbs up and also consider subscribing to my channel. And also you can download the slides and schematics I use in my videos from my website at thefearlessengineer.com. The link is coming up now in the banner. So thanks for watching, have fun and see you next time here on The Fearless Engineer.